All right, hello, good afternoon. Welcome to those of you joining. We'll give it a few minutes for people to get on the webinar and then I'll do an introduction. Those of you joining just now, we're going to give it a couple of minutes and then we will get started with the webinar. Thank you everyone for being here. Hey, let's go ahead and get started. Good afternoon. Thank you for being here today and welcome to the third session of the Energy Modeling Deciphered for Architects virtual workshop. This is presented by AI Virginia's Committee on the Environment, and today we'll be discussing optimizing energy models in a successful team. My name is Delaney Ogden, Director of Education for AI Virginia, and I'll be the host helping with presenting the webinar today. Just a few housekeeping slides before we get started. We will have the chat feature available to you today. So please feel free to engage with others on the chat, maybe put your name out there. Let us know who all's on the webinar. Let us know where you're located. And then after the presentation today, we're going to have a Q&A portion. So this is a time for you all to ask questions in our Q&A tool of the presenters. And yeah, we'd love to engage with you. So please be thinking of those questions for our presenters today. If you're having any connection challenges, just remember to remain on Zoom. Zoom does a really great job of trying to reconnect those that get disconnected. And then for optimum bandwidth, just make sure that your background apps are closed. That will help a lot. After the session, I will also be sending a survey, so please take some time to give us your feedback. We greatly appreciate knowing what you thought about the workshop. Next, we have our LU slide for continuing ed. Today is approved for one AIA LU HSW, and these credits will be reported within 10 business days. And like I mentioned before, we'll have a short Q&A period after the presentation. This is our moderator and speakers for today. And now I'd like to turn it over to Kat Smith, who will be moderating the session. Kat?
Thanks, Delaney. Hi, everyone. My name is Kat Smith. I'm an architect with Graham & Parker Architects up in the Northern Virginia area. I'm just going to give a quick introduction for our session and our speakers today. So this is the third and final AIA Virginia COAT webinar series for 2024. Hopefully you were able to see our previous two sessions, but if not, those recordings will be posted on YouTube, the AIA Virginia YouTube, hopefully soon. They're not up quite yet. But today we will be talking about optimizing energy modeling and creating a successful team around energy modeling. You might recall if you were here last time, we talked about the Sketchbox program. So we're going to add a couple more programs onto that and hopefully build on that knowledge. So consider this a Energy Modeling 201 or 301 class. So today we have two wonderful, talented speakers for you today. One is Sean Sobolowski, who is with James Posey Associates, and he is the Sustainability and Building Performance Project Manager there up in Maryland, and he has about 9 years of experience and is a registered professional engineer in the state of Maryland, and is also a building energy modeling professional through ASHRAE and a LEED accredited professional for building design and construction, and has managed over 50 building projects certified with LEED or Green Globes in the DC, Maryland, Virginia area. Mickey Chapa will also be speaking today. If you were at our previous sessions, you might have seen him before, but he is an architect and building scientist at Payette out of Boston, though he's worked up and down the East Coast, including Virginia Beach, so some of you might see a familiar face. So with that, I will let them take it away.
All right, good afternoon, everyone. And we are going to jump right in here. Share my screen. Excellent. Okay, and here are learning objectives for today. We are going to talk about the different modeling cycles and where you hit the necessity to be looking at energy and analyzing your buildings. So quickly today, we're going to go over two different tools that we can use, building on the Sketchbox exercise that we saw in the last session. And then along the way, we're going to talk about different ways that we can interpret and question those models. I mean, part of our task is really learning how we ask questions, how we really dig into what the data is telling us. Is it accurate? Is it does it make sense for the building project type and use? And are we improving on it with subsequent iterations? And then the last thing, looking at the major modeling cycles across project development. So just a quick overview of what is an energy model, right? What we're doing is we're tracking energy in and energy out. This is a graphic of just some of the really incredible science that's out there right now on climate, and the topic is that we can monitor all of the energy that's going onto the Earth's surface, and then what's reflecting, and then we can know the difference. A quick graphic tip as we talk about energy processes is I would always recommend to keep your legends the same. What it looks like in this graphic is that the energy out is much more significant. So we're going to touch on that with our energy models, but I just wanted to make a note of that. So how does an energy model work? We talked about why it's being used. We'll see how it gets used in the design process, but this is a quick graphic to show that an energy model is just simplifying all of the different physical interactions that are going on, whether it's the air temperature inside, the resistances that are going across your building surfaces, and then all aggregating in. And that's including the radiant temperature, the wind speed, the solar radiation that's coming from the sun passing through our windows. So how that is simplified is really important, and how we set up those relationships, again, can alter or affect our results that we see. So this graphic at the top is an Open Studio model, and you'll kind of notice some of these colors that are standard for that software that was developed by the Department of Energy, roof, ceilings, walls, windows. And one of the really important parts here is that it's being reduced to planar surfaces. All the windows are in line with those planes. If you try to make a curved geometry, the software will probably reinterpret that as a bunch of triangulated meshes, and it gets really, really challenging. So an energy model, kind of fundamentally is not a design model. There is some processing that has to happen, whether that is done manually by some of the shoebox tools that we're going to show today, or whether that's done by more sophisticated embedded modelers that are now coming on the market. For instance, one of the tools that we're going to look at today is pollination. This is a development of, again, you can see the Open Studio interface, and this program will work to, adapt to different Revit geometry. So this is another path that's out there. We're going to be looking at a much simpler version of this, just to try to get used to some of the tools. And then a key some phrasing as we'll go through these models is this term adiabatic. So when we're looking at doing a shoebox model, like what's very important to be able to adapt the scope of our study, right? Like, do you need to do the whole model? If you have a 4/1 apartment complex, maybe you just need to do a typical unit on like at the roof level or at the podium level, and then maybe one also in the middle. And then you can start to test different assemblies as opposed to running a full model, because it takes time. Like there's actual, process time to take into account as you increase complexity. So simplifying that, and maybe turning off some of those spaces. So for instance, this term adiabatic is deciding which walls or surfaces that you're not going to be including that are negated from energy transfer. So it's another thing to think about while we're building a model. So, and the other software that we're going to look at today is Climate Studio. So I think these are probably comparable in their functionality. Climate Studio has a little bit more intuitive of an interface, whereas pollination is free and allows you to evaluate the same amount of, quantity of information or types of analyses. So we're going to go through. We'll have to provide these links to folks otherwise, but I'm going to go through the download splash pages for each of these products, and then also these are some other learning resources I'll highlight before we get into our demo. But however, this why are we doing the shoebox model is always kind of key to remember, and also key to deciding on what tools that we want to use and whether, what avenues are opened up for us by the decisions and which tool sets that we use. So I think, coming from an architectural background, it's like very valuable to me to be able to understand where the energy is being lost. Like, can you connect it spatially to the ideas that you're presenting? Is it going out of these windows? Is it going more out of the floor? See, for this particular example, I've turned the floor, the ceiling, roof structure off. So we can just check the different faces or walls. And also the effect of daylight and sunlight on the model and how that relates to energy performance. So those are all like very important functions to be able to have in your tool set. So I think as you're maybe evaluating things for your office, these are questions to keep in mind. And then also to be able to evaluate things seasonally. Maybe you only need to understand your worst month in very, very high detail to reduce your peak loads. So, okay, we'll move on to our energy model now. So I'm going to flip open some of our resources. Are you all seeing the Climate Studio website?
Yes, we see it.
Excellent. Okay, so on this product, I know this is being used by some very sophisticated energy modelers, such as Patil A10, other teams, and it comes with a very easy to use interface, in my opinion. And so you would go to a download. I would recommend downloading version 2. And I'm going to provide a script that is used. So this software interfaces with Revit and with Rhino as well. The Revit exporter is just for daylight, and then all of the other energy analyses are performed in Rhino. So I'm going to open up Rhino, and hopefully you're familiar with Rhino and the Grasshopper interface, or maybe someone in your firm, a younger staff might be. But at the top, hopefully this is large enough. I'll expand it so we can see. But so we've opened up Rhino, we've opened up the Grasshopper kernel inside of it, and we see the Climate Studio. So there's a lot of different parts and pieces, but conveniently, this software has a a whole template. So that's what is included in the top left. So you can select the analyses that we want. And you can see there are a lot of different things that we can study. So for today, we're looking at thermal analysis, and there is a shoebox energy model. So if I just select this right now, we're going to see all of this spaghetti populate onto our dashboard. So I'm just going to, just so you see, very similar. I've added in some other components for clarity in the file that I'm going to share with you all today after this meeting, but a couple like high level things of what's included in a digital energy model. Let me see if we can kind of go back to our side-by-side view. Is that you have the geometry, right? So you have the components that you're looking at. This is all this geometry is baked into this file. So part of that is we have to assign the windows, the walls, the shading structure. That can be done multiple ways. You can do that either by building up as individual faces, in which way that you would have a lot more control out of what each of those components are made out of. But then there's also, most of these softwares will have construction sets. We saw that with Sketchbox, so that you could choose a ASHRAE 2019 compliant kind of collection of assembly types, you know, R values and such. And then you also have to identify the location. So this luckily popped in, and there is a nice interface where you can just click on this button to search for a weather location. And that's, you know, we could look for, let's say we'll look for Richmond, and we can grab the weather file for Richmond, Virginia. So that's, now that's loaded in. We can change the program. So for this little exercise, we're going to test just changing a program and what effect that has. So we'll do a multifamily residential, and we'll just hit OK. And then this setting, this zone setting, a lot of these programs similar between the pollination software that we'll show next and the Climate Studio is that you're really just there's a lot of, you know, flow from one element to the next, but just so long as you're kind of lining up the names, you can generally search for it and find it pretty readily. If not, there are other tools, YouTube sites that you can look up for the given software. So I've just connected the program that we selected and dropped it into this energy zone. If I can't find it, sometimes you can just search for it. So Climate Studio, energy zone, and you know, maybe that pops up with the component that we need. And for this case, all we're going to do is just hit this run button. If it is working, you should get a command prompt that opens up. And in this case, it ran pretty quickly. So just again, within a couple minutes here, we have some test geometry. We can start to look at different performance qualities of this space with a very large window, and its energy balance. So this was the quick note that I made about the globe and the energy in and energy out. So an energy model is balancing losses and gains, and then, you know, for the particular systems that we're looking at in a shoebox setting, when you don't have maybe the exact, in this case, if we don't have the exact building systems that we're going to use, that's probably another package that we could look at in one of those other template files. But this is just an what they call an ideal air system. So it's assuming no energy is created or destroyed, and you're just tracking the gains and losses, say, across the envelope or across the building systems. And then you can start to look at, you know, identify the biggest transfers of energy. So we have heating, we have cooling systems. In this case, the environment and infiltration should be pretty high for the residents. But now if we compare that, sorry about the back and forth here, let's just say this is also probably looking at it in metric. It is looking at it in the metric UI. However, for the sake of looking at this, we can just compare it relatively if we change the program, let's change it to a science lab. And then rerun it. So this is calculating in the background. And then we can see a much different energy spread. And the last one, it maxed out about 1,500, and now this is saying 6,600. So, we have a 4 or 5-fold increase in energy uses by program. So, again, things that we know, but now that we can see that this can help us make recommendations and dive in deeper seasonally and based on different components. So that's Climate Studio very, very briefly. So the next thing that I want to open up is a honeybee or a pollination script. So where do we get that? One last thought on Climate Studio. There's this really wonderful course that's put on by the team that developed that software. It runs in March through June. It's like $200 for the full course. Really high level comprehension of sustainable building design. Definitely recommend. Next, is this pollination software. So this developed, in full disclosure, part of the team that developed this software came out of my office. So I'm very grateful to be kind of a part of this, part of this community. But again, I'm happy to share this with you today because the tools that they have baseline are free. And then there are a lot of other things that can be added on with cost. But so you have to create a login to see sort of like this next collection of tools. But when you log in, there's a download section. When you create a login, you'll get a free trial to begin with. So the Grasshopper plugin is free and open source. Hopefully, if you have students or new hires that are just out of design school, hopefully they're teaching this in the universities now and environmental building systems classes. And again, just because of the cost barrier to entry is so low. However, there are a growing number of tools within this group that are available as plugins for Rhino and for Revit, but we're just going to look at the free Grasshopper ones today. And what are we looking at? So in this family of tools from the pollination set, there's this collection of animals. Ladybug is the climate analysis software portion. Honeybee is the energy software. Dragonfly is an urban energy modeler. If you're looking at district systems, just pretty fascinating. And then Butterfly is a very simple CFD interface. So inside of this tool set on this resources page, there are some example files. And again, maybe this might be a little overwhelming. This is going to redirect you to a GitHub page where you download it. So not quite as slick as the Climate Studio templates package, but there are a lot more of these scripts that are available online and designed around very specific analyses. So we're going to look at, if we opened up this core example file, that's just what is Grasshopper, what is Ladybug, how do they work together. So there are these three files. Oops, sorry. And this model creation workflows. That's how do you build the model? What does a honeybee model look like? So if you clicked on this, it's gonna kind of drop down into another folder. And then if you hit view raw, it'll download it. So you can see that file is downloading. So we're pulling up what I've selected to go through today are some core example files, as well as the energy example files and a shoebox model. So these are if I opened up the energy example files, it would pop open to this page, and then we're going to be looking at the shoebox energy model, which is down here. And again, downloading, opening these up, it's free. You can start to toggle back and forth and get a little deeper understanding of how the tools might work, and some very simple analyses that you can build into your workflow immediately. So let's go back to Grasshopper in our Rhino interface. And this is the model creation. So just like in Honeybee, or excuse me, just like in Climate Studio, we see the same coloration of the Open Studio faces, so we know that that's kind of like running in the background. And we can model that by individual faces, so we can have a lot of control over, this is actually like the walls, the windows, the shading. And then this is one of the things that I think is really important for, architects. We're just never happy with the black box situation. Like some of the older, some of the other tools that are on the market, you don't know exactly how that is being processed. With the software like this, like you do know, at the cost of making sure that you are, really in control of all of the different pieces, which takes time and experience. But it does even allow you to, change different radiance parameters. So that is the ray tracing software. Also note on the download, when you download Ladybug or Honeybee, it's going to download Python, it's going to download Open Studio and Radiance, which is the ray tracing and the light tracking software that's kind of underneath of all of these other tools. And sometimes actually, when you do download it, it may take you opening Grasshopper once or twice as it loads in those different kind of background softwares. So in this case, this energy model, so we're looking at one that's designed by face, which is, again, just like plane by plane construction, similar to how we saw in Climate Studio. And then this model from Solids, that is if you just drew a box. Let me see if I can turn this off real quick. If we just had a box and all of these different little rooms inside of it, what does that look like? So again, slightly different collection of geometry that was included in each of these little sample files. But what we're looking at here, just to walk through the spaghetti again, is like we have our geometry that's being put in. It's being translated into this honeybee room object. Similarly, there's this collection of modifiers. So we need to add the location, we need to add the constructions and the program. So these are two different methods for kind of attacking the same questions and the same line of options. In this case, the geometry for the windows is extra planes that's added on to the coplanar with the surface of the box. It's a really important thing. And then we can inspect the different elements. So I'm actually going to go back to, let's see, if I just want to make sure that my windows are not showing up. So I'm going to hide this piece. And I just want to look at the walls. So this is one way I can make sure that I know that the windows are being cut and tracked through. So you'll be shared this script. This is a lot to take in all at once, but I just wanted to show you some of the functionality that is available in these free tools. And then another method that is presented in this sample file is, how do you do it a whole floor? If you're like, okay, well, I've really dialed in different space types, different orientations, then you can connect lots of rooms together and then start to process a whole energy model. In our practice, we do this very, and we'll talk about this later, very rarely. And what we, would be looking at are just smaller shoebox, like one room, maybe a key atrium or signature space, or really dynamic space from a thermal perspective. So, okay, so this is a file set up just to how do you build the model? How do you put it together? And you'll get a copy of this. So secondly, now I want to show you just how do you go through and add some qualifiers, put some adjectives on these spaces and walls and things. So if we were looking at, let's find our model again, just our little tiny house example that was presented. So again, this is one of the this is a shoebox energy model, and then I've just added some comments on here. So if you have the time, you can go through and look at it. But we have the different faces, the windows, and we can add qualities to that. So one of the ways that you can add a characterization of your model is through this construction set. And we have within here, I think I was doing a demo in the Boston area. So we can change the climate zone. We can change a building vintage. I think the Sketchbox tool only had the current ASHRAE model. I think this is a really nice tool if you're looking and want to compare an existing building. It has a lot of historical time series or time steps in there, and then also the construction sites. So a little less clean of an interface as compared to Climate Studio, but again, I think very valuable in terms of its cost, and it's free. So as we track through here, we have some different properties. We have construction sets. We can change the program. In this case, we'll do the same analysis. I have this one set up so that we should be looking at it in imperial units. And the Honeybee tool set also has this collection of this like search feature where you can then look at all of the other programs. It kind of works the same way. They have a search programs, search construction types, search individual materials. So you know if you dive in, you can look at building up your own assemblies, which is also the facility to do that. I think is very, very helpful. So then all of those constructions and programs get applied at the room level. And then shades can be added. This could be context buildings are also included in the shade. You can choose whether they're attached or detached. Okay, so that is how to set up the model. And then the simulation, this is, again, probably maybe in the weeds. Hopefully you'll be able to have a chance to go through and look at some of these other resources. If you had multiple rooms, you would have to pass it through this kind of adjacency thing, so the software can know which rooms are touching, and then you can decide, oh, okay, well, I want this to be, maybe it's a multi-zone open air, let's say cafeteria or large atrium space or something, that you could decide whether or not it has an air boundary. Does it actually have a wall in between it or not? So this allows you a high level of flexibility and functionality to dive in and to how your model is working. Again, adding in shades. So you go from a room into a model, and then it gets passed into this Open Studio model, so this OSM feature. And in this case, again, you can control not only just like very standard generic processes, but you can control what you want to analyze, whether you want to do the zones, or if you're specifically looking at the energy flow. I showed that graphic of heat flow through windows or heat flow through walls. So you can choose whether or not you want that included. Maybe this is too much detail for your particular practice, but I do want you all to be aware that this is out there. This is also a pretty interesting thing. So Climate Studio had a nice graphic where you could just search for climate files. If Honeybee has an online service, this should be opening up my browser window to a map of climate files, hopefully quickly. There we go. So we could click on any one of these places anywhere in the world that have documented their climate data. So again, another really useful feature. And then you can inspect it with other Ladybug tools about hourly, monthly averages, that sort of thing. So that's the setup, and then we could run it, and we'll look at coming to the end here. So you can see I have analysis that's already been run, but we set this to true, we run it, it does the same thing. I can turn it off, I can run it again just so you can see as an example. And again, it's kind of loading everything in the background. Hopefully this doesn't take too long now that I'm also streaming this video here for you. But yeah, you can see again, it's processing, it opens up a command prompt. And then still thinking, here we go. So same thing. And then this tool also allows us to like really dive into like what are each one of these loads, and how much are they. Honeybee also kind of collects the data into these little packets where it works kind of like a database if you're familiar with database design, where there's a header and then a long list of data items. And so if you want to look at the data, it kind of comes in as this hourly collection, 8,760 values, and that's every hour of the year, and some information about it. And then these are the loads in particular that are coming from the cooling in kilowatt hours. So, you could use that, compare it to how much kilowatt hours you're collecting from PV panels. So a lot of functionality within here. There's some other little notes in the margins, but when we look at our model, then we can see the same thing. Let's see if I can make this full screen and have the same level of detail pulled from that. So I'm gonna have to pass this over back to Sean, but we'll be sharing these scripts at the end.
All right, thanks, Mickey, and thank you everyone for joining us today. Appreciate the high level overview and refresher of the fundamentals of energy modeling from Mickey, as well as the software demos. We're going to pivot now a little bit to energy modeling cycles through design all the way to post occupancy, and hopefully I can provide perspective from an engineer and helping you all with energy modeling application in your practice and on your project. So let's just dive in. So I actually want to first share a question my colleagues and I had received recently from an architect we work with, asking how we include energy modeling in our scopes of service and when we don't. And this particular architect had indicated the owner, once the service, does not want to pay. And I really think this illustrates well the importance of recognizing that energy modeling really starts before design. And what that really means is, right, we have to understand how do we use energy modeling from really early design analysis with massing studies and the demos that Mickey provided with simplified modeling. And I'll point out, you'll hear me use simplified modeling. That's really interchangeable with shoebox modeling, really intent to represent early phase design energy analysis. But as you move through design, right, you have load reduction, modeling, life cycle cost analysis, and you get into higher performance analysis with geothermal well field sizing, net zero energy design, sizing PV systems. And then you could use energy analysis to help pursue utility incentives and then even demonstrate compliance for code purposes, energy code purpose. And for those of you that have worked on LEED or other certification, third-party certification, energy modeling can come into play there to help earn points. And beyond design and construction, you have monitoring-based commissioning, which energy modeling can play a part in. And there's many more applications. I think it's also worth noting that energy modeling is actually just one tool in a broader category of environmental analysis tools. But today we'll be focusing on energy modeling. And I think that recognizing a project-specific requirement is important in helping identifying the analysis tools and team members that are going to be necessary to fulfill the project requirements, goals, and any targets that have been established. From an engineer's perspective, I can tell you that at a base level, going into almost every project, understanding the energy code implications of the scope of work really drives the conversation of, right, are we pursuing prescriptive or performance-based compliance? One example I'll use is we had a particular project where an architect wanted to pursue a design that had a really high glazing percentage that was above the prescriptive allowances, and that shifted the project scope to necessitating an energy analysis. And as I mentioned, third-party rating systems and pursuit of any sort of sustainability certification. You can have integrated process credit, for example, from LEED that specifically requires simple box energy analysis early in design. Late in design, you also have the option to pursue prescriptive-based compliance or performance-based compliance. So these are additional considerations when you start to consider a project scope. And I think with the focus on climate in this day and age, high performance building design is becoming more and more critical in what we all do. Right, we're starting to see a lot more net zero energy design and making sure that the additional design effort that goes along with that, right? Geothermal well field design, estimating the solar generation required to achieve net zero, all adds effort, and the analysis tools and team members that are required to help support those targets. So now, excuse the wrong way there. Now diving into modeling cycles. So as I mentioned, we're going to kind of broadly cover energy modeling cycles from design through construction and then into post-occupancy. ASHRAE standards are the American Society of Heating, Refrigeration, and Air Conditioning Engineers, published Standard 209, which defines the modeling cycles through these phases. Starting in design, there's 7 different modeling cycles that span from conceptual design all the way through construction documents phase. With starting in conceptual design phase, we have simple box modeling and conceptual design modeling, which transitions into load reduction modeling. And we'll get into these in a little bit more detail. In my practice, I would describe these first 3 cycles as generally what I think the broader design community would consider simple box or shoebox modeling. And then further transitioning into design development, we have HVAC system selection modeling, and this typically supports life cycle cost analyses. As design continues into construction, we have design refinement, design integration and optimization, as well as energy simulated aided value engineering. So looking at these first 3 cycles, simple box modeling is really when we're first evaluating building geometry and site orientation. And again, as I mentioned, I think there's certainly a lot of overlap between these cycles. Conceptual design modeling, maybe once site orientation's nailed down, conceptual design modeling is really intended to represent when form and architecture of the building are in development, right? Are we looking at a rectangular form or an L-shaped building? Have we started to think about the envelope construction types and performance, which then transitions into load reduction modeling and really starting to hone in on reducing annual energy use and heating and cooling peak loads with thermal performance values and other load reduction strategies such as shading. So kind of diving into the coordination requirements that I think are important to highlight, right? What kind of information do energy modelers typically need from architects if this is something that's not being handled in-house? Ajit had provided this really useful graphic in the previous session, so I figured I'd build up on it with the inputs, right? Weather, envelope, occupants, plug loads, lighting, HVAC, water heating, and utility rates. Envelopes really, I think, the big one. If I'm working with an architect, really understanding what is the anticipated performance of the envelope for a project. And I will note building geometry and operation schedules are 2 other inputs not listed here. Geometry kind of follows, right? We really can't do any sort of energy analysis if we don't know what what the building looks like. And then it's also worth noting that there are also inputs that really need to come from owner input, such as, right, how is the building expected to be used in terms of people and plug loads? What are the utility rates expected to be? And operation schedules. That's certainly an owner item. But so what happens if the design's not is at a point where you don't have answers, particularly with respect to the envelope? I can tell you my typical approaches would be starting with code minimum performance. And another resource that I highly recommend is the ASHRAE Advanced Energy Design Guide. The code's pretty straightforward, and it's always a great fallback, particularly for new construction or addition work. Right here in Virginia, the current energy code, you can pull all the opaque assembly performance values and fenestration performance that would be required. And again, like I said, high performance building design is becoming more critical with climate continuing to be a focus. ASHRAE has published advanced energy design guides for various building types, and they range from a 30% energy guide to 50%, all the way to what I would describe as 100% of the way towards zero energy. And they're free from the ASHRAE website. I've provided a link, and they're really valuable. They provide numerous recommendations on strategies for achieving high performance building design, including envelope recommendations, targeted U values, R values, solar heat gain coefficient values for high performance design. And I often turn to these guides as a resource for making recommendations, because at the end of the day, I really want to stress these envelope performance values are really an energy model input that needs to come from you all, because you're the ones ultimately responsible for designing the envelope. Because if I had it my way, the glazing percentage on most buildings would probably be a lot lower than I think what most of you would desire. So another graphic I wanted to reshare from Ajit's previous presentation was this side-by-side comparison of compliance and predictive energy modeling. Just to re-illustrate, compliance energy modeling is really talking about like lead energy modeling, where you're comparing your proposed design against a fictitious baseline to evaluate the performance to achieve some amount of points towards a sustainability rating. Predictive modeling, on the other hand, is high performance design. How is the design actually going to perform in the real world? So going back to how the owner is ultimately responsible for providing operation schedules, I just want to juxtapose with compliance modeling. A resource that I would lean on for operation schedules, again, is ASHRAE 90.1 Users Manual provides typical operation schedules for various building types. And this is a great fallback for compliance modeling, right? It gets the job done for a lead energy model. But when we really start to talk about high performance building design and you're targeting net zero, it's critically important that the building's actual operation is accurately captured in the analysis. And that's where it's important for you all, as typically primes on job, to recognize that this is a really important coordination item, that an owner really needs to weigh in on the anticipated operation of a project. And here's just an example. Middle school, we worked with a project owner to understand the anticipated operation across various space types. And to just jump back, right, the default school occupancy here from the user manual, it's one occupancy schedule that's intended to be applied across all space types, which really lacks a major degree of precision when you're talking about developing predictive energy analysis results. So moving on in design, this brings us to design development. And HVAC system selection modeling. So as I mentioned, this is really kind of where we get to life cycle cost analyses to compare different HVAC system options that are still being developed. And I'm going to quickly share here just an example report. I'll zoom in just to illustrate what you might expect to see from an engineer. So it really provides a brief overview of the project, kind of high level discusses the inputs that went into the model. Again, with a life cycle, we're ultimately trying to inform system selection. So all of these inputs for internals are held static because it's really about understanding the difference in performance across the various systems, which is why as we move through the report, we kind of define what the different systems are that are being evaluated. Here's a table representation of those systems and how they vary. Report then gets into the different costs, right? We have energy costs, the initial equipment investment costs, the ongoing operational and maintenance costs, which leads us to ultimately the results. And for this particular report, we had a supplemental ASHRAE 90.1 compliance calculation and ultimately our recommendations. What would typically accompany this report are all sorts of input and output reports from the life cycle cost analysis software, as well as the energy modeling software, and all of our supporting calculations for the costs. And I'll mention that included in all of that would actually be EUI data. I can tell you that I as an energy modeler, I often get a slew of emails towards the end of the year when you all start to begin tracking down your AIA reporting data. So it's something to be aware of, that data is often in reports that you might have received for a particular project. So I'm going to quickly hand this off to Mickey.
Sure. Yeah. Thanks, Sean. Yeah, and just with that, we'll always from the architecture side, we're going to be looking for the EUI for the reporting, but that's not the only consideration that we have. Is are you also providing a water budget? Do we know how much water is being collected by the site? And that seems to be also like within the realm of the MEP engineer or the energy modeler to be able to kind of collect for us and to be able to express for the project whether or not certain systems are appropriate. Maybe if you have a cooling tower, right, that is going to be part of that the energy systems and resources that are available for the project, the budget. So yeah, lastly, MEP system, embodied carbon, I think that's on the horizon, and then tax incentives. So Sean, thank you.
All right, thank you. And going to be mindful of time, so we can leave a little bit of time for Q&A. So something to just be aware of, right? Mickey covered some great demos for simple box modeling. We're at this point kind of transitioning from SD into DD and CD. So simple box modeling, typically you see really simplified geometry, and it becomes much more detailed when you shift to space by space. And along with that, a lot of our other assumptions get refined. Occupancy, plug load, you go from very general assumptions to very detailed assumptions for simple box and the more detailed models. With the shift into construction documents, we start to get into design refinement. I would describe this as like preliminary lead energy model. If you're pursuing lead, this is a really good time to check in with your energy modeler or engineer to kind of see if the project's on track with the lead certification target. And then design integration and optimization, as well as energy simulation aided value engineering are another great construction document applications, which ultimately brings us to as designed energy performance, which is really taking the final design documents, right? That's ultimately what a lead model typically represents. Additional cycles would be, right, energy analysis can be used to support change orders. And then after construction, as built energy performance, right? Any changes that resulted through construction could again be captured through energy analysis to provide predicted energy analysis of a building before there's actual operational data. And I think one of the important coordination items when you get into these later stages of analysis is important as architects to recognize that the design documents really need to clearly identify the envelope performance values. This was just an example of a spec that wasn't clearly identifying the R value of the board insulation. Similarly with the glass, this actually did a good job of identifying the assembly glazing performance versus the center of glass, which is oftentimes an overlooked detail. And then to kind of wrap it up is post-occupancy modeling. Right after you have operational data, you can really kind of go back and trend the actual performance against predicted performance and see how if the building's performing as it's expected to. Again, this is just an example from one of my projects and how our model data compared. It was by the third year of operation pretty close. And again, this similar like for LEED, you might see this in application with monitoring based commissioning. So that's it. We'll hopefully left a few minutes for.
All right, thanks
Q&A.
guys, that was great. I think we have time for one question, but you can see both Mickey and Sean's email is up here, and you are also, we welcome anyone to reach out to AIA Virginia COAT Committee on the environment. If you don't know, hopefully you do, with questions as well, and we can forward them, or we are a great team that can maybe answer them ourselves. So our question is, would you consider compliance modeling for third-party certifications, or just to confirm to owners how their building should theoretically be able to perform as a modeling cycle?
So the compliance modeling, I think that they can kind of be lumped together, right? I think with and I'm going to jump back here to the as design energy performance. I think it really serves both of those purposes, right? When you have a full set of design documents and you're doing a detailed space by space model, that if it's set up as a predictive model, and I guess I'm going to contradict myself here, it really, they are separate. The compliance model for LEED purposes is developed in accordance with Appendix G of ASHRAE 90.1. So there are a lot of assumptions built into the guidelines for that standard that do not support real world performance of a building. So I would actually decouple if an owner is looking to really kind of predict utility bills. It's a more detailed analysis where again, that the operation schedules need to reflect the owner's expectations for operation rather than default schedules that might be permitted for a LEED compliance model.
Okay, great. All right, so we have 2 minutes left, so I will just once again put in a plug for both AIA Virginia COAT, but also there are a number of COAT chapters among the various components. So if you're interested in joining, learning more, please reach out. Delaney, any last words?
No, just to say thank you for everyone joining. And yeah, we're excited that we were able to do this with VA COAT. So thank you everyone so much.
Awesome. And thank you, Sean and Mickey.
Absolutely. Thank you.
Thank you all.
Thank you.
Bye, everyone.